I want to figure out how to just do a beginner style parser in JavaScript. Welcome back to Creative Coding with Maxime. Today, I'm going to show you something that I've been working on for myself. So I make my own tools, and I use these to produce the kind of renders that I make for my own creative coding. And recently, what I've been working on is a WebGL to JavaScript transpiler. So what that means is I can take WebGL code, and then I can parse it, and then print it out again in the shape of JavaScript. And then I can execute it in a JavaScript context. And I can even write basically a pixel shader, and I can output that to the screen. So what does that mean? If I take the standard start code from WebGL, from ShaderToy, it gives you this lovely gradienty rainbow thing going on. I copy that and I put it inside my GL parser function. Then here in my engine, if I save it, boom, same output. Alright, so I'm sure you're wondering why I would do such a thing, and I'm going to explain that in the next video. However, today, what I want to talk about is that to do this, I needed to be able to actually parse the WebGL. And I'd known about parsing, and I'd tried stuff like that before, but trying to figure out how to do this in this setup, I found it very difficult to find material that could adequately explain, or just that could explain how to set up a simple parser. Like, you can find a whole lot of theoretical stuff and some stuff that's probably based on being really optimized for doing loads of code and whatnot and professional setups, but I just wanted to do a sort of beginner. I want to figure out how to just do a beginner style parser in JavaScript. And so after having written this, I was like, wait a minute, now that I figured out how to do this, I might want to just share with people what I've made, because I think it's quite straightforward. And yeah, I think it's nice for that information to be out there. So we're not going to write an entire WebGL parser today. What I want to start with is just a simple arithmetic parser. So what that means is just little sums, something like 5 plus 5, and then also so we want to do plus, minus, multiplication, division, and we want to have support for brackets. So there's a couple of interesting challenges in there, and yeah, I'm very excited to share that with all of y'all. Alright. Okay, so I've got a tool here called Quokka, which allows me to write JavaScript and show the return values of variables, which is super useful. And what we're going to be doing today is we're going to be trying to parse an arithmetic expression. And essentially, we want to be able to do something like this. And then have our parser parse this expression, and then actually execute it as well. Tell us what the answer for this should be, what should come out of this. You'll notice that we've got brackets here, which is the coolest part of the challenge in my opinion. But yeah, all right, let's start simple. 1 plus 2. Okay, so how does a parser actually work? First of all, the input here is a string, and we need to turn this into something called tokens. Tokens are a representation of everything that we have here, but instead of just being a character, we need to specifically identify it. And for arithmetic expressions, this seems a little trivial, but this stuff makes more sense when we get to other more WebGL stuff. Alright, so first thing we want to do is we want to write a lexer. Alright, and this takes a script object, and what we're going to be doing is we're going to generate tokens from the lexer, from this expression, calling it a script here because it's going to turn out to be a script, but yeah, you get it. And if I write the word tokens here, Quokka will tell us what the values of tokens, and currently it's undefined. Makes a lot of sense. Alright, so first thing that we're going to be doing is we're going to be removing all the white space. This works for expressions and in most languages. That's why you have to do semicolons for at the end of the line. So if you remove all the white space, this is like spaces and like new lines, then you can still parse the whole thing. JavaScript is a bit different because you don't necessarily have to do this, but luckily we're not parsing JavaScript. Alright, so first thing we're going to do is removing all the white space. So let's make another function for that. Remove what? Oh. I'm not going to pronounce what I mistyped there. Okay, so how do we do this? We use JavaScript's replace function, and we can give it a regular expression. And yeah, we're going to be dealing with a bunch of regular expressions. Don't worry, they're not too complicated, and I'll try and explain them as best as I can. But yeah, that's definitely a part of writing parsers. So how do we do this? Well, if you do 2 slashes, it makes a regular expression. Okay, so the regular expression here looks for /s, which means white space, and we put a G behind it for global so that it doesn't just find the first one that it finds, but it just finds all occurrences of white space. And then replace it with nothing. Alright, cool. So, and then we say script equals remove white space script. And then if we, and now you can see it's 1 plus 2 without any white space. Alright, now, the way that the lexer works is that we're going to be looking at all the different characters, and we're going to see if they match a specific regular expression. In fact, we're not just looking at every character individually, but however long this could be. Currently, again, because it's arithmetic, this doesn't matter as much, because everything that we're going to be doing is just going to be a single character. Actually, no, that's not true. The numbers can be more than a single character, because obviously you can have 100, so it's 3 characters. Anyway, we'll get to that. So, the way that we do this is by setting up a list of rules. And we're going to be using the rules, we're going to check against the rules in order to see what kind of token needs to be generated given where we are in the script right now. Okay, so first what we want to do is we want to define a match. So this is going to be another regular expression. We're going to use the caret here to denote that we want to look only at the start of the string, meaning to say that we're only looking for the first token that we can find. And what we're going to be doing here is, well, the first thing, one is a number. So we're going to write a regular expression for numbers. And for now, we'll keep it simple and just write it like this, which says any number character, and then if we put a star here, that should say 0 or actually we'll do a plus 0 or more. Alright, let's see. Yep. And then with the match we will describe what kind of token this is. And so in this case it will be a number. Alright. I'll write the second rule as well. So that would be for the plus operator. So again, use the caret to say that we're only looking at the start of the string, and then what we can do is we can do a plus. Yeah, I think we have to escape it here because plus means something on itself. Yeah, alright, that makes sense. And then, yeah, I think that's it. And then I'm going to call this expression op. Op is for operator, and the reason why this is an expression op is because it's an operation that happens at the expression level. I'm sure that's not particularly clear, but it'll become clearer later when I explain what the uses of this. But for now, you can just know that the expression op is, in this case, the plus. It's also the minus, but one thing at a time. Alright, so what we want to do is we're going to be generating some tokens. So we'll make an empty array. And then, the way we do this is we take the script as it is, then we find the first match, and then we take however many characters that match is. So if it's a longer number, it'll be more than one character. And then we'll remove that off the start of the script, and then we'll continue with the rest of it. So basically we like eat bits off of it. And this is because this way the caret operator will only look at the first bit, and we'll be looking at the next token because we've taken off the first token that we've been able to identify. How do we do this? We'll do a while loop, and we'll say while script.length. I hope this is not going to get stuck in infinite loops because Quokka is executing all the time. We'll see. While script.length. We're going to be looping through all the rules, and it is actually important what the order of the rules is. Again, not explicitly now because of just doing arithmetic, but this definitely matters later when we're trying to identify IDs versus keywords. We'll be looking through the rules, and we'll see if this is actually a match. And the way that we can do that is by using the match function, which takes a regular expression, which is the one that we just put on the match. So we check the current value of the script that comes in, if it's either a number or if it's the plus operator. Alright, I'm not sure what it's complaining about here. We'll figure this out. Okay, yeah, nice. So, match will return an object that tells you about what it matched. With regular expressions, you can match specific groups. You can get different stuff out of it. But if it doesn't match anything, it just returns null. So if we check for if, we'll be like, hey, did it actually match something? If that's the case, let's get the destructure the rule. Restructure the kind from the rule. So we know that we matched this regular expression. So then what kind are we talking about? Did we match a number or the expression op? Then we can get the actual value of what's been matched from the match array. This is an array which will tell you, which will hold multiple groups, but in this case the first one should just be the value that we matched against. And then we will add this token to our token array, making an object with the property kind and val, and then we'll do that eating thing off the start of the script that I was describing before. So we'll do a slice. Let's see, we start at alright. Sorry, I was just looking at my reference code to figure out what was happening. So slice actually returns the new value. I guess we could do, yeah, oh well. So what that means is we'll want to tell it what we want, what of the string we want to have left. So we'll start at the length of the value that came out, meaning to say that if we matched a expression, it would just be a length of 1 because it's just a plus. But if it's a number, it could be longer, right? Take that length, and then we go to the end of the script, and boom, we slice that bit off. Script turns into that. Yeah. Could probably write that with a splice as well. Oh well. And then what we want to do is we want to let's see. Yes. Like I said before, the order in which we match is important, and so we basically want to when we find a match, we basically want to reset our for loop, and the way that we can do that is we can add a thing called a label to our while loop here. So you would usually do something like break or whatnot, and that breaks out of the main loop, out of the first loop that you're in. But now we want to kind of jump to the start of the while loop. So we'll give this a label called loop, and then we type continue loop. So this will stop the loop from the for loop, go back to the while here, and start from the beginning. If we ever make it through all of the rules without matching anything, meaning to say that continue loop wasn't called, then we're gonna wanna break, because otherwise we'll get stuck in this while loop forever if we cannot actually figure out what the token is that we're looking at the start of the string. Alright. And then all we have to do is return the actual tokens, and boom, would you look at that. So what's happening here is we get an array with 3 values. The first one is an object that's a number with the value 1. The second one is an expression op with the value plus. And the third one is a number again with the value 2. So that's exactly what we see here. Alright, cool. So before we extend the thing, let's actually let's continue. Let's continue. Okay, so now that we have a list of tokens, what we want to do is we want to write the actual parser. And the parser, what it's going to do is going to look at the tokens and figure out a structure that it can use to execute the expression. Execute basically means to make the plus operator apply 1 to 2. And so the way that we do this, the parser, it will actually produce a thing called an AST, an abstract syntax tree. And that is a tree structure that we can recursively traverse to apply these operations and make sure that they happen in the right order. And what that means we'll get to back later. We'll come back to later as well. So let's see. We're going to make an AST, and we're going to get this from a parser function where we input the tokens. Okay, so now the parser function. Alright, so what's going to happen here is similarly to with the Lexer, we're going to go through this list front to back. However, instead of like eating it like we did with the string, which was kind of necessary because it's a caret match, instead we're going to be holding an index to tell us where we are in the parsing step. That way we can, it's a non-destructive operation, so obviously it's more performant, but also means that you can look backwards, look forwards, whatever. Like, make stuff easy. So what we're going to do is we're going to make an iteration variable that starts at the beginning. Then what we want is we want to be able to get the current token that we're at. So we'll make a function called current. Yeah, I'm writing them as lambdas here. And I'm defining these functions here inline so that they have the scope of the whole parser function. It's kind of like a React style way of doing things. Anyway, I like it. How do we get the current? All we have to do is we have to get the token at the index. Alright, seems simple enough. Then what we're going to need is we're going to need another function called accept. And what accept does is it will look at the current token and it will see if the kind of that token is equal to the kind that you passed to the function. And if that's the case, it will increase the iterator, meaning to say that we've kind of eaten it, but instead of like fully removing it, we just move the iterator over. And then we'll return true or false based on if it happened. And yeah, if the token is not, if the kinds do not match, then we do not increase the iterator, and then we just return false. So how do we do this? Well, we use the current function we just wrote. We'll check if the token's kind is not equal to kind. I should probably do this. Question mark here is in case the token doesn't exist, it doesn't have a kind property, but we'll just, in that case, it will resort to null, which means that it will always turn out to, the if statement will turn out to be true, meaning to say it will not match and we return false. Otherwise, we increase the iterator and we return true. Alright. Yeah. So, how does this work? First of all, we're going to parse this as an expression. So we're going to make a function expression that can parse an expression. Alright, I've said the word expression a lot now. So actually, before we get to writing the expression, we're going to make one more helper function, and this one is very similar to accept, but it's called expect. And expect will practically will check if accept happened, and if not, it will throw an error. And this means that we're at a bit in the parsing where we can for sure say, hey, this is the token that we expect, and if that's not the case, then we can error because we know that the syntax is incorrect. And that could be useful for when you have an opening bracket and you don't have a closing bracket. And there's nothing really that the parser can do to figure out what to do because there's just a bug in the code. Alright, so how does this work? First we'll get the token from current, then we'll check if it actually accepts the kind. If it doesn't, yeah, we're gonna throw that error. Let's say expected kind got, and then we do token.kind, again the what's the operator called? I'm thinking with the question mark. In case it doesn't exist, then it just says got undefined or got null, and we'll tell it the index of where in the token list this actually occurred. And so that will give us hints as to what's wrong with our code. And if not, we're going to return the, so if it does accept it, we're going to return the token's value. And that's just for easy use later on. Let's actually make my correct. Hey, okay, look at that. So in this case, what do we expect in an expression? Well, first off, we expect a number. So what we're going to say is const left equals expect number. Actually, let me think about that again. I'm so sorry. What we're going to do is we're going to make a function that actually parses the number. And this one expects there to be a number. So we'll get the value from it. And what we're going to be doing is we're going to be returning an object, which is our node inside the AST, so the abstract tree syntax that we're going to be generating. And we're going to construct this recursively as well. And so the number function will return the token, or will return the node inside the tree that will help us ultimately do the execution. And so we're going to give that a kind again. And we'll give it a value. Okay, this is not to be mistaken by the tokens. They look very much like the tokens, but they're slightly different because they're nodes inside the tree. And you'll see later why it's a tree, because a number does not have any children, because it's just a number. However, an expression does have children. Namely, it has a left side and a right side. And so what we're going to do now is we'll say const left equals number, then expect expression op, and this is why we wanted to call it expression op, because this is both for plus and minus. We'll add the minus later, but it's essentially the operation that belongs to what we call an expression. We'll do multiplication and division later, but those are called terms, and that uses then the term op. So first we get the left hand side, then we get the right hand side. So as you can see here, basically we're just moving through the list of tokens, saying that, well, first we've got a number, then we're expecting the expression op. If that one's not there, then we give an error because we don't know what's going on. Then the right hand will again be a number, and this we will return. This will return as a node with the kind op. In this case, we don't have to separate expression op and term op because they'll both be operations within the execution time. Then which operation exactly is it? That is the value. So the expect here returns. Here, let's get it. Op. Yeah, sorry. All right. So we get it from the expect, and then we return the left and the right. Okay. So now that we have these functions, remember we're still in the parser. We actually want to parse this, and so the way that we do that is by returning a call to expression. Alright, let's see if that worked. Hey, would you look at that? Okay, this one's a little harder to read than the list because the list is obviously just in order, but here we go. So first thing that we'll find is the root of our AST. The root node is an operation, the plus operation, which has a left hand side of a number with the value 1 and a right hand side of a number with the value 2. Alright, that's super cool. We can definitely work with that. And now let's get on to executing this AST to figure out once and for all what 1 plus 2 actually is. Who knows? It'll be a surprise. We'll do a drum roll. But let's not get ahead of ourselves. So let's get the result by executing the AST. Alright. Let's write the execute function. Here I'll just say node because we'll reuse the exec. It's a recursive thing again. Alright. What we're going to be doing is we'll just get a node and we'll get the kind of the node, which is either an op or a number as we wrote it now. We'll do a switch statement on the kind, and we'll do number first. That was easier. I like to use brackets in switch cases, not exactly necessary, but when you define variables with which you also define in other cases, then it won't complain about redefining an already existing variable. Okay. So because it's a number, we'll get the value out of the node, and then we'll return that value. This is still a string though, so we'll use plus string. If you do plus before a string, it'll turn it into an actual number. It'll parse it as a number. And so when we execute now, in fact, we can actually check this. If we just do 1, then okay. I would have thought that would work. Actually, oh yeah, because we're only parsing expressions. Okay, let's not. Okay, let's not do this yet. No worries. Yeah. Okay. In that case, we need to define the operation node, and in this case, we'll get the operation to the left and the right from the node. Then we'll do a switch case on the operation because we're gonna be having more, but now all we have is plus, and if it's plus, then what we'll do is, and this is the recursive bit, we'll execute the left side and we'll do plus execution of the right side. Okay. Yeah. Let's fix my yeah. Technical Practically speaking, we don't need it. We just do a default of don't know. Okay, and then let me see. All right, I figured it out. I was being silly. I forgot the keyword case here. All right, hey, there you go. Well, that was supposed to be a drum roll, but okay, yes, we figured out finally that 1 plus 2 is 3. Wow, what a surprise. All right, other numbers works too. Can we do longer? Oh, look at that. Nice. Okay, that's cool. Well, I hope that makes sense. Let's let's fill it out more. So we'll do a minus, and look at that. Expected expression op got undefined at index 1. And as you can see, the lexer is lexed up until what it understands, but then it just returns. And so we only have the 5 here because it doesn't understand the minus. So how do we add that? It's very straightforward. We change this. Let's see if I can just undo this. Alright, so if you put stuff between square brackets, it makes everything inside it like an OR. So it's OR plus or minus. And then let's see, and now boom, it can actually tokenize or lex the minus sign. Yay! The AST also has the operation there. And then now we just need to write the implementation. So we'll add minus, and then we'll do a minus. And now 5 minus 2 is 3. Yay! That breaks, but that works. Alright. Cool. Cool. Now we want to do multiply. And you might think it's just as easy as adding the minus to the plus. However, there's a thing called operator precedence, which means precedence, whatever. Yes, one of those. And what that means is that there is a difference between if you first calculate 2 plus 5 and then multiply it by 10, or if you first multiply 10 by 2 and then add 5. And the correct order is obviously 10 times 2 first, and then plus 5. And so the way that we take care of this within our parsing is that, and I already alluded to this, we have a expression, which is something with a plus or a minus. And then we have something called a term, which is something with a multiply or a division. And we can use the recursive nature of a parser to express this within the order that this gets turned out. And so what we're going to do is here where we expected a number, instead of expecting a number, we're going to expect a term. Alright, let me go to my example code. Yes, alright, cool. And then the term is very similar to this, but here it expects a term op. And yeah, that seems to be about it. And then the expression, instead of expecting numbers, we're going to be parsing terms. Alright. What you might have noticed here is that this here assumes that we have terms and, well, we'll work on that assumption first. So what we're going to do is we're going to add the term operators, which is essentially the same as the expression. However, now we do divide and multiply. So let's make that term up. All right, and then so I guess the way it's set up now is like this. Okay, so it manages to parse this because in our current setup we say we have an expression, which is something with, for example, a plus, and on the left side there's a term, which is something with a multiply, and on the right side there's also a term, could also be divided. And this works, this comes out right. However, that's obviously a bit cumbersome, so we want to be able to check if what we're dealing here makes sense. And so the way that we do this is that if instead of expecting the expression up here, we're going to see if we can accept it. And if we accept it, then we can go on and parse the right side because we know that it's an expression. If there's an expression with the left side and then the expression operator, then we know there must be a right side. However, if that's not the case, then we will just return whatever the term returns, because in that case it could just be a term, because we're not dealing with an expression, not a plus or a minus, but instead we might be dealing with a multiply or a division. And so the way that we do this is, this was a nice setup here with returning the value from the expect, but because accept returns true or false, we're going to have to get the token out of this beforehand. And then this will be a token of val. I mean, if that's the case, right? So accept expression up. And if that's not the case, then we will just, as it's telling us here, it's just 3. Oh, is that 2? I don't know. I'm not exactly sure what that is. All right. Then we will just return the left side. All right. And what that means is that while we look for an expression, if all that we have is a term, the first thing an expression will do is see if there's a term, and then it will have a look and see if there's an actual expression op. And if not, it will just return the return value of the left hand side, which in that case could still be a term. If that's not the case, then it will find the right and then return its own node, which is then the op, and we use the token here that we got from the current to be able to tell what the actual operation was. And we have to do that beforehand, because if it does accept the expression, then it'll go one index further. All right. Let's see if that actually works. So what that means is that if we just have this, then that should parse, and it does. It just misses the execution. So let's add those. And yeah, and boom, 10 times 2 is indeed 20, and 10 divided by 2 is indeed 5. And then let's see, can we do plus 5? Expected term op. Right, because the terms cannot, okay, yeah. Okay, so we've got more work to do. Seeing as the expression and the term are very similar, I'm just going to copy this one again. And just say term op. And then the left hand side is a number, and the right hand side is also a number. And what you see here is the same trick. So if first we're going to look at it and be like, hey, is that an expression? And then and first it looks at the left hand side, which can be a term, which you'll find here, and then it'll be like, oh, it's not an expression because there's no plus or minus. Then it'll look at the expression and it'll be like, then it'll look at the term and it'll be like, is this an actual term? So in case that we do 10 now, it's not even an actual term because it doesn't have the term operator. There's no divide or multiply. And so then again, it will just return the left hand side, which is just the number. And so now we can also parse the expression 10. Look at that. Isn't that nice? All right. And so let's see. 10 plus 5 divided by 10 is indeed 10.5, and not 1.5, which would be the case if you added the plus beforehand. Yeah. So what that means is that operator precedence here is adhere to 30 plus a half, right? All right. Now, the final thing that we want to be able to do is obviously go against those by adding little bracket boys. And of course, we don't really get very far because we don't know how to parse these yet. So let's figure out how to do that. It's actually pretty straightforward. We're going to match these separately because we're looking for opening brackets and closing brackets in different places. We're only looking for closing brackets once we've found an opening bracket. And so, yeah, it's essentially, oh wait, we don't even need these. Yeah, so the slash here is to escape the character, and now we've got a opening bracket, and we'll just call it bracket open. All right. Same thing here, but instead we'll do a closing bracket. Bracket close. All right, coolio. Now let's see, can we lex that? Hey, look at that. It's able to lex the brackets. And now we're going to parse these. So how does this work? Well, this again is the cool power of all of this being very recursive, kind of fractally, I guess you could say. I keep thinking of the word fractal, but I'm like, no, it's actually recursive. I mean, like, who knows? Yeah, sorry. What am I doing? Yes. The way that we do the brackets is, yes. So I called this number now, and I think we're just gonna run with that name. It doesn't exactly make sense, I guess, but I think it should be fine. So what's gonna happen now is when we look for this, please let me know in the comments if you know a nicer name for this than number, because we're not just looking for numbers, we're now also going to be looking for expressions within in between brackets. So the way that we do this is first we check if we're actually dealing with a bracket. So we'll do an except for bracket open, and if that's the case, we know we're in bracket land, and instead of expecting a number here, we're going to be parsing the expression within the brackets, and then we're going to be returning that. So how do we do this? Well, quite simply, we'll get the body of these brackets, and that's another expression. Okay, and then we'll do an expect, because if you don't close your brackets, you shouldn't really expect anything to work. Haha, pun intended. Okay, and then what we do is return a node for the AST that we'll just call brackets. Again, please let me know if you have nicer names for this. Some of this stuff makes sense, and some of it is a bit awkward. Okay, and now we have a node that tells us the body, and that's another expression which we can then execute again recursively. So now, in the place where we're looking for numbers, we might be looking for, let's see, did that actually work? I'm gonna guess no, because it shouldn't be 0, should it? Oh yeah, we need to execute the brackets actually. So what's gonna happen if we find brackets? Then we will get the body object, which is the expression, and then we'll return the execution of the body. And boom, look at that. 45. Alright, so yeah, 3 times 15. Oh, that is actually not yet correct. I got so excited. Let's see what is going wrong here. Do we actually have? We do have it. And then here we go. We've got You can see the plus there. Left, right. Oh, you can't actually look inside it. Oh, that's a bummer. Too bad, Quokka. You were pretty good. Well, let's make it simple. That works. Wait, let's make an expression that's easier to figure out. No, that's clearly not working. And I can tell you why. Wait, first just check if the brackets work. I made it too complicated by adding the other one behind it, but that's the last bit we'll actually be looking at to fix. So, yeah, let's first see, this works. 10 times 10 times 10 plus 5 is indeed 150, and if we were to remove the brackets, it would be 105. Alright, well, you see the power of brackets. Awesome. Okay, well, what was up with this? Why was this not working? For the same reason as that this is not working. So, we can do 1 plus 2, but we cannot do another plus. And the reason for that is that an expression, the way that this stuff works is it keeps going sort of deeper into whatever the thing is that we're parsing. And if we do plus plus, then use two pluses, then they're next to each other, and there's nothing actually looking into what is next to this. And so we could write a little loop here to check for the stuff, but I found a really elegant way to do this actually. And the way that we're going to do this is that in the case that we have something like this, when we have an expression and then potentially another expression behind it, what we want to do is we're going to take this expression, pass it into the function that looks for the expression as an already constructed left-hand side for what's going to come after that. So what that means is then our expression function can be passed a left-hand side, which we'll use instead of checking for another left-hand side. And then we will call this, wait, I'm just gonna show you. Here we go. So, yes, we are going to be able to pass, left, if there's already a left, then we're gonna use a nice, null coalescence operator, is that the word? So, if left exists, use left, otherwise check for a term. And then the way that we're going to chain this all together, what is actually going to call this expression with the with that left-hand side is the return value here. So if we actually evaluate another expression where the left-hand side that we return is the currently parsed expression, then it'll recursively go down the list and put the next expression in the left-hand side of the put the previous expression in the left-hand side of the next expression. All right. Let's see if that actually worked. Nope. Okay. So let's see. What am I doing wrong here? Is this running at all? Maybe I should look at that. Why is this finicky? Here we go. Hey, okay. So left has already been declared. Okay, there we go. Yeah, because it's a const here. Hey, my bad. Okay. Thank you, terminal. I will put you down a bit more now. And boom! Here we go. 1 plus 2 plus 3 is 6, and we've been able to calculate that. Now, we want to do the same thing, the same trick with the term. Is really just the same thing. So let's forget not to pretend this is a const. Left for this, and then we return. This way we can chain. So before we were trying to chain a multiply and a divide by, and we should now be able to actually do that. Let's see. 1 times 2 times 3 is 6. Yeah, that makes sense. Divided by 3 is 2 divided by 3. Yeah, that makes a lot of sense. And what if I do 5 plus 5? Let's not make this too hard on ourselves. Hey, yes, okay, yes, obviously. Yeah. 3 times 10, 30 divided by 10 is 3. Oh yeah, we literally just made it so 10 divided by 10. Okay. Oh wow. Cool. Alright. Well, that's it. I hope my explanation is clear. I'll put the code of all of this down in the description. And yeah. I'm honestly quite happy with how compact it is because, yeah, like I said, I was trying to look for resources on how to do this and everything looked so complicated. I was like, hey, what if you just had like a straight up example that made it pretty clear? And yeah, this setup is strong enough to parse, I'm not going to say the entirety of WebGL because I haven't done that yet, but at least enough to, like I demoed in the start, to run the start template code from Shaded Toy. Yeah, and we'll be talking more about how to do that in the next video. Alright, bye!